Hello, Assalamualaikum. My name is Sharul Iman bin Jumidah from B09211028 today I will introduce my friend Mohammad Ainol. Please introduce
So
yourself.
my name is Mohammad mustaqim. My registration number is B0921102114.
My name is Andrew Lucky Thomas. My metric number is B0921103337.
Today we going to represent free body diagram from actual structure. So first we go to what is the rigid body? Rigid body is the idealization of body that does not deform or change shape. Formally, it will define as the collection of particles with the property that the distance between the particles remain unchanged during the course of motion of the body. New aspect of mechanics is to be considered here is that the rigid body under the action of the force has a tendency to rotate about the same axis. Thus, in order that a body be at the rest, one not only need to be ensure that the resistance force is the zero, but one now must also ensure that the force acting on the body do not tend to the rotation. This issue is addressed what is the follow. Now, I will introduce you the free body diagram. What is free body diagram? Free body diagram is a 3D from the actual structures painted. Free body diagram is a useful aid for the represent of the relative magnitude and direction of all force acting upon the object in the given situation. The first step in analysis and describe most the physical phenomena involve the carefully drawing of the free body diagram. So, free body diagram is actual pen from the actual structure from 3D perspective. The size of the arrow body diagram show that magnitude of the force while the direction of the arrow denoted from the force action. Movement. The movement of the force is the measure of the tendency to the cause of the body to rotate about the specific point of axis. This is different from the tendency of the body to move or translate in the direction of force. In order for movement to develop, the force must act upon the body in such a manner that the body will begin to twist. This occurs every time of the force is applied, so it does not pass through the center of the body. A moment is the dual force do not having a equal or opposite force the direction along the line of action. I will give to Andrew Thomas for the present.
Yeah, thank you, Muhammad Aiman and Muhammad Iman. This
Sharul
is
Iman
the actual structure of the cooling tower, which we measured last week. Next. From this diagram, we can know the assumptions. The structure is in distribution load. The support is also fixed. The weight is around 686.7 Newton. Distance shoulder is about 1 meter. Next. This is the 3D free body diagram of the cooling tower. Next. This part is I'll pass to Iman Mustaqim.
So, okay, I will explain about the calculation. Refer to the free body diagram. We know that the cooling tower stay at one point, so it only has the value at the k, which is on z axis. So the w we get is equals to 0i plus 0j minus 686.7 k. So after we get the w, we need to find the unit of the vector. Before we find the unit of the vector, we need to find the position of vector and the magnitude first. So for the position of vector, For BA and BC, we get negative 0.35 I minus 0.35 J plus 1.42 K for the BA, and for the BC is 0.7 I minus 0.35 J plus 1.42 K. After we get the position of vector, we also need to find the magnitude, which is we get for the BA, we get 1.5, and BC, we get 1.62. Then we can get the unit of vector by dividing the vector and the magnitude. Then after we get the unit of the vector, we need to apply the answer into the equation of equilibrium, which is summation of fx equal to 0, summation of fy equal to 0, and fz equal to 0. After we get the forces of the three axes, which is x, y, and z, we need to find the moment. We need to know that the formula of moment is equals to force times by distance. And the first moment for M1, we get 0.33 I minus 0J plus 0.08 K. And for M2, moment number 2, we get 0.31 I minus 0.0J minus 0.15 K. And for the moment 3, we get negative 240.35 I plus 240.35 J plus 0K. Not then we also need to find the vector of the gravity, which is we get 0.35 I plus 0.35 J plus 0K. Then after we get all the value of the moment and the gravity, we need to apply it into the equation equilibrium of moment, which is summation of m equal to 0 and m1 plus m2 plus m3 equals to 0, and we get the answer as below. Okay, next slide. Next. Okay, for after that, we need to find the I component and K component. First equation we get is 0.33 FBA plus 0.31 FBC equals to 240.35. Then the second equation is 0.08 FBA minus 0.15 FBC equals to 0. And the third equation, if FBA equals to 0.15, FBC equals divide by 0.08. Okay, after we get all these three equations, we need to start substitute the third equation into the one equation to find the force for BC and BA. And we get the answer for force BC, we get 775.32 Newton, and for FBA, we get 1.53.73 Newton. And after this, we also when we have substitute the value into the equation equilibrium of us, which is before slide, we get fx, fy, and fz, right? We get the three equations. So these three equations, we need to substitute the forces that we get in the one in I component and K component, and we get all these three answer, which is for AX we get 6.78 Newton, for AY we get negative 163.7 Newton, and AZ negative 1376.62 Newton. The answer is negative because our plane is moved upward, but the forces of the cooling tower move downward. So the answer is negative. Okay, that's all for the calculation.
Ah, that's in the conclusion, by drawing the free body diagram, we know we can deliver equilibrium in the Cartesian vector for the force. We can identify how much force to use actual force used for the actual structure using the equation equilibrium. For that's all from us. Thank you.
Thank you, sir.
Thank you.